to present our speaker today, Stephen Morris from the Department of Economics in MIT. Stephen's research focuses around foundations and applications of game theory to mechanism design. He has lots of achievements. He's a member of the American Academy of Arts and Sciences, a fellow of the Econometric Society, former president of the Econometric Society, past editor of Econometrica, but probably one of the greatest achievements of Stephen is the huge number of students that he had. I counted 79 PhD students, which, okay, I mean, twice, no, not twice, but many more years than I have. So, Stephen, when 120, I mean, we say in Hebrew, so I hope you reach 120 students soon. Anyway, today, Stephen will speak on implementation via information design in binary action supermodular games. And Stephen, the Zoom room is yours.
Okay, thank you very much. It's a great pleasure to be talking to you guys. COVID is no fun, but getting to talk to a wider, having forums like this that allow you to speak to more people who you might not ordinarily get to speak to is one nice side benefit. So I'm going to talk about this, which is joint work with Daisuke Yoyama at the University of Tokyo and Satoru Takahashi at the National University of Singapore. I welcome questions during the talk. I have a zillion slides, but I don't plan to get even close to getting through them. I just want to tell you about one theorem, basically, and questions about new stuff or clarification about the literature that I'm building on, whatever. Just ask questions, and I'm very bad at following things on Zoom, so if you can just unmute and shout out a question in the middle of when I'm speaking, that'll be the way to ask a question. Okay, so what do we mean by all these, this long title? So here's some background. What do we mean by information design? Suppose you fix a game and you ask the question, what outcomes, by which I'm going to mean a joint distribution over action profiles and payoff relevant states, what outcomes can be induced by picking the information structure? So how can you change outcomes by choosing the information structure? Assuming that you also, of course, the games have multiple equilibria, so assuming also that you can pick the equilibria. Okay. We call that partial implementation from the mechanism design literature. That's what we say. We say partial implementation when you get the right outcome if you get to pick the equilibria. Okay, now this problem has been much studied in recent years and is sort of well understood. In particular, it has the feature that it's enough in providing information to the players to simply provide players with action recommendations that they have an incentive to follow. And those incentives, Meyerson a long time ago called them obedience constraints, constraints where you want to follow the recommendation of a designer. Okay, the set of obedient outcomes, so the set of outcomes that are incentive compatible that a designer could induce by choosing the information structure, corresponds to a set of correlated equilibria of the original game. We're going to be talking about incomplete information setting, so it's a particular version of correlated equilibrium we call Bayes correlated equilibria. Okay, so, and this is the many player generalization of the Bayesian persuasion problem, which has been, which you've probably heard a lot about in the last 10 years. Okay, as in mechanism design, or you can see this as a branch of mechanism design, in fact, one appeals to a revelation principle because the designer gets to pick the equilibrium. That is to say, we do not need, in studying the partial implementation information design problem, we do not have to worry about every conceivable information structure directly. It's enough to think about information structures where you simply make an action recommendation to the players, where the recommendation to the players, where the signal the players observe is just an action. Okay, so this is kind of the background for the talk. As I go through, I will give definitions and some review in words of this background in case you don't know it, but I hope you'll ask me more questions about, the stuff on which we build at any point in which it would be useful. Okay. All right, but what about this paper? This paper is going to ask the full implementation question. So we're going to say what outcomes can be induced if you get to pick the information structure, but you don't get to pick the equilibrium. Okay. This is a distinction that happens in mechanism design. Let's think about what's the information design analog. Okay, so you can't appeal to the revelation principle, well known. Nonetheless, we're going to be able to give a complete characterization of full implementation by information design in a special case of binary action supermodular games. Okay, so we do need extra structure, but then we get a characterization that's actually not so far from the partial equilibrium characterization, and that's kind of nice. Okay, here's a second question. What outcomes can be induced if you can pick the information structure and expect the smallest equilibrium to be played? Okay, intuitively, this is somewhere in between partial and full. Okay, because we're looking at binary action supermodular games, of course, there is the smallest equilibrium we can talk about. It will turn out that this is an easier question to pose and answer than the full implementation question. Actually, once you have the smallest equilibrium implementation characterization, the full implementation version is easy extension. And actually, for many applications that people have become interested in, information design applications where you have sort of min-max preferences with respect to the information choice, it is smallest equilibrium implementation that is most relevant. So actually, the focus of both this talk and the paper will be on smallest equilibrium implementation, although full implementation, as I said, is kind of a corollary. Okay, any questions about the questions?
Stephen?
Yeah.
What do you mean by smallest equilibrium implementation?
That assume that I give the players the information structure. They're playing a binary action supermodular game. That means that the set of equilibria are ordered in the incomplete information game.
I see, okay.
And I'm assuming that they play the smallest one.
Okay, got it.
Okay, so our main result is going to be that under a dominant state property, that is, there exists a state where one action is going to be a dominant strategy, an outcome can be smallest equilibrium implementable if and only if it satisfies not only obedience, that was the basic condition for partial implementation that I mentioned, but also sequential obedience. Sequential obedience is going to sound a bit like obedience. It's going to be a strengthening. Of course, it must be a strengthening because it's a more demanding requirement. Okay, and what is sequential obedience? Sequential obedience says, think about the designer making a recommendation to the players. So, think of the players starting out playing the low action. There's two actions. And the designer makes a recommendation to players to switch to the high action in some randomly chosen order. The players don't know, they know the probability distribution over states and orders of recommendations, but when they receive their recommendation, they don't know which order they're part of. Okay? And sequential obedience is going to require that the player has a strict incentive to switch when told to do so, even if he thinks that only players before him in the sequence have switched. Now, he doesn't know who's before him in the sequence. He's just forming a conjecture based on his knowledge of the distribution. Okay, so this is more demanding than obedience, because in obedience, you want to switch knowing who else is going to be told to switch, assuming that they're going to follow the recommendation. Here, you only expect the people before you to switch. Okay. So, okay, so a nice thing about this is that it's a nice finite linear program. People did assume that it's a very badly behaved object, but it's a bigger linear program than you need for partial implementation, but it is going to be a finite linear program. Okay, and full implementation, of course, you could do smallest equilibrium implementation, you could do largest equilibrium implementation by symmetry, and you basically just need a reverse sequential obedience condition going the other way is what you need for full implementation. So I won't say anything more about full implementation today. All right, so I'm not really going, in the paper we discuss some applications of the result. I'm going to focus my talk just on describing that main result, and I probably won't have a lot of time for applications, but let me just briefly mention them. One question that a bunch of people have been studying recently is, might be called information design with adversarial selection. So that's saying someone picks an information structure anticipating that the worst equilibrium for them is going to be played. Okay, we can use our characterization to prove results about this problem. Okay, so in particular, we show that if a game is a convex potential game, so it's a potential game that satisfies the convexity property that translates into saying that payoffs are not too heterogeneous, then if the designer has monotonic preferences, in other words, he always wants a higher action to be played, then we can show that the optimal outcome satisfies a perfect coordination property. Either everybody is playing 1 or everybody is playing 0 in the optimal solution, and the optimal outcome is easy to characterize. Basically, it corresponds to finding the highest probability event where everybody playing the high action on that event just maximizes the potential of the underlying potential game. Okay, and we also talk about what happens if you add bonuses. Okay, so this is just to say that the sequential obedience characterization does not directly tell you anything about particular games, but we can use it to solve problems that people couldn't solve before. And maybe I'll say a little bit more about that at the end. Okay, so let's talk about the literature. One observation is that something that it took me a little longer to realize than it should have done, a little embarrassing, since I spent a lot of early years working on a literature that might be called the higher order beliefs literature. What can you say about what happens in a game as a function of beliefs and higher order beliefs? It turns out that that literature is the key to answering this question. And let me explain to you at a high level why that's the case. The arguments that we're going to give are a development of ideas in that literature. So you may recall that Rubinstein and Carlson and Van Dam, in different kinds of ways, but in closely related arguments, showed, one way of saying it is they showed that it was possible to fully implement, that is to guarantee that it got played in all equilibria, to fully implement the risk dominant equilibrium of a 2-player binary action supermodular game by choosing the information structure and perturbing the payoffs a little bit. Okay, so Rubinstein said there's a small probability event that somebody has a dominant strategy. If I choose the information structure correctly, I can guarantee that the risk dominant action is played everywhere. Okay, not how he phrased the result, but that's an interpretation of the result. Okay, so various literature built on that. A 1997 paper that I had with Atsushi Kaji showed, among other things, that you couldn't implement the non-risk dominated equilibrium in a 2x2 game. It gave further characterizations and showed that you couldn't fully implement the non-risk dominated equilibrium. A literature followed on robustness to incomplete information. It's actually closely related to the whole global games literature. Last year, my co-authors published a paper in Econometrica, which characterized robustness to incomplete information in binary action supermodular games. And this is closely related to full implementation. Okay, so a high-level description of the connection is that we're taking ideas about full implementation that were implicitly in this older literature, and we're extending them to incomplete information settings to answer this question that people got interested in from a completely different angle. Okay, this literature, you perturbed payoffs a little bit in a complete information setting. In our incomplete information setting, we won't have to perturb payoffs. We just have to assume that the set of payoffs are rich enough. And then full implementation is going to reduce to designing the type of information structure where you get a unique outcome. Okay, now there is a literature in the last few years looking at information design with adversarial equilibrium selection. Let me not go through this in detail. Let me just say that in these papers, people look at more specialized settings and find particular information structures that that fully implement, or smallest equilibrium implement, an outcome. Basically, we're doing it for a more general setting, binary action supermodular games. Our information structure is a canonical one that fits all such games. It's therefore more complicated than some of the, so a contribution of some of these papers is that it gives much simpler information structures that will induce certain outcomes. Okay, and with that introduction, I'll get onto my model. Any last questions? Okay, so suppose there's a finite set of players. It's a finite set of states. There's a common prior on those states. Full support common prior, let's say. It's a binary action game, so let's call them actions 0 and 1, which will be held fixed. So the action profiles are just profiles of zeros and ones. Playerized payoff is going to be a mapping from action profiles in the state to the real line, and we're going to maintain a supermodularity assumption in payoffs, in actions. So that means that if we define the payoff gain that individual I gets from choosing action 1 rather than action 0, can you see my cursor, by the way? Okay, so his payoff gain from choosing action 1 over action 0, when other players choose A minus I and the state is theta, supermodularity, of course, just says that this difference is going to be increasing in A minus I. And as you know, all that's going to matter for payoffs of the game is going to be this difference. For best responses, it's going to be this difference rather than this. So I will end up using DI and UI interchangeably to describe a player's payoffs. Okay? So that's the game. That's we call it the base game, the underlying game. Oh, and we also have a maintained assumption that there's a dominant state, which means that there's one state, theta upper bar, at which even if everybody else is playing the low action 0, every player wants to play action 1. He gets a gain from playing 1. So it's a dominant strategy at that state. If you knew the state was theta bar, you would have a ex post dominant strategy to play action 1. Okay, so that's the base game. It's all of the game except for the information structure. So now let's describe an information structure. So we'll have a countable set of signals for player I. So T is just the product of the signals. And we'll have a common prior over signals and the state, which we'll call pi. Okay, without loss of generality, we'll assume that every type has positive probability. And the information structure, which is this object here, is going to give rise to a Bayesian game. And for Bayesian game, we know how to define Bayes-Nash equilibria. A strategy is a mapping from signals to polar distribution over actions. And I see that I didn't write down the definition, because you know what the definition of Bayes-Nash equilibrium is. Okay. Now, I said that we're going to be interested in the set of outcomes. We're not interested in the information structure per se. We're interested in the joint distribution over action profiles and states that can arise. So any information structure combined with a strategy profile is going to induce a joint distribution if we simply integrate out the signals. That's what this is saying, taking the summation over T, and then there may be some randomization by the players under their strategies, but there will be some induced joint distribution over actions and states. Okay, so that's the game. And now let's talk about the partial implementation literature. So we'll say that an outcome nu is partially implementable if there exists an information structure and an equilibrium such that nu is induced by that equilibrium with that information structure. Okay. We'll say that the outcome satisfies consistency if the outcome has the property that the marginal on the states is equal to the original marginal on states that we took as part of the description of the base game. We'll say that an outcome satisfies obedience if it has the feature that if players were simply given an action recommendation without being told anything about the state, they would have an incentive to follow the action recommendation. And a known result is that an outcome is partially implementable according to this definition if and only if it satisfies consistency and obedience. Okay, consistency is just a accounting check for the probabilities. The important thing is obedience. Okay, the reason why this is true, depending on where you're coming from, you can think of different reasons why it's true. At one level, it's a simple generalization of Aumann 1987 when you add in these extra states theta. So then this is just a generalization of Aumann 87's characterization of correlated equilibrium. If you're coming from a mechanism design perspective, this is a sort of basic revelation principle argument that it's without loss of generality to let signals be action recommendations. If you had an information structure with more complicated signals, you could simply add up all those contingencies where a different action was being played. Okay, so Dirk and I call these outcomes Bayes correlated equilibria. And they're pretty nice objects, okay, because it's a like correlated equilibria. They are correlated equilibria. It is a linear program, so you can characterize partial implementation by information design very simply. Any questions on that background stuff? So now let's design our new questions. So smallest equilibrium implementation, because the game is binary action supermodular, well, actually, because it's supermodular, there will be a smallest Bayes-Nash equilibrium, sigma bar, which will in fact be a pure strategy equilibrium. Okay, that was pointed out by Milgram and Roberts and Vives and I don't know, in the early 1990s. Okay, so it's well defined. We'll say that an outcome nu is smallest equilibrium implementable, S implementable for sure, if there exists an information structure such that that information structure and the smallest equilibrium corresponding to that information structure induce nu. And we'll call the set of such outcomes the smallest equilibrium implementable outcomes. It's going to turn out to be an open set, interestingly. So we're also going to discuss the closure of the S implementable outcomes, and we'll call that SI bar. So look out for that distinction. Okay. All right. So let me give an example. I'm just going to illustrate a few points during the talk with this example. It gets a tiny bit complicated to come up with a minimal example to make my points. So although that looks a little complicated, it kind of is the minimal example to make some of my points. So let me just explain how we get there. Consider a game where there are two players and they have to decide whether to invest or not invest. And if you don't invest, you get a payoff of 0. What's your payoff to investing? Well, it's going to depend on the state. If the state is bad, your base payoff to investing is negative. It's -8. Okay. In the good state, it's going to go up. We'll give you a bonus of 9. So your payoff to investing in the good state goes up to 1. In addition, the payoffs are asymmetric, because I want an asymmetric example. So if you're player 2, you'll get an extra bonus of 1 for investing. And finally, we want supermodular payoffs. So we're going to give you a bonus of 3, other things being equal, if the other player invests. Okay, so those are the features that are built into this example. Okay, this example does have the feature that you have a dominant strategy to invest if you know the state is good. Both players have a dominant strategy to invest. Both players have a dominant strategy to not invest if you know the state is bad. Okay, but the interesting question is, what can we partially implement or fully implement if you have some mixed information structure about the states? Okay, so this was the games here. Let me assert, suppose it was the case that what you wanted to do is you wanted to give the players an information structure that would maximize the expected numbers of playing and investing. You wanted to get as many people to invest as possible. Okay, I'm going to assert that this is the best thing that you can do. This table below gives a probability distribution over outcomes. I should have said, by the way, that the good and bad state have equal probability a half each. Okay, so I assert that the best that you can do is, look, if you're player 1, you get a payoff 4 from investing in the good state if the other player invests, and -5 if player 2 invests in the bad state. Okay, so if both players always invest in the good state, because there's no reason not to, 2/5 is the highest probability that we can put on player 1 investing in the bad state, because then his expected payoff, conditional on investing, conditional on receiving a recommendation to invest, will be 0. So you couldn't get more than 2/5 here. But player 2, who is more willing to invest, it turns out he will be prepared to invest even when player 1 doesn't invest, because we gave him this extra bonus. Okay, so this is the best thing that you can do, the best thing that you can partially implement. Okay, Ariely and Babichenko, maybe I saw Ariely here, have a paper where they talk about binary action, Bayesian persuasion, and they do an extension to strategic games. And one observation is that because of the asymmetry, the optimal outcome is going to be asymmetric. You're going to get the player who is more willing to invest more often. Okay, but this is not the unique equilibrium. Okay, we found the best thing that you can do exactly by making player 1 exactly indifferent between investing or not investing when he was told to invest. So we've deliberately made it knife edge, and there's definitely going to be a strict equilibrium if you just give players recommend to invest and not invest, in which they both never invest. Okay. Okay, I'm going to assert that the following outcome is smallest equilibrium implementable. If I take some positive eta, I can get both players to always invest in the good state, get both players to invest in the bad state with probability a little less than a quarter, and to both not invest in the bad state with probability a little bigger than a quarter. Okay, I mentioned that that was an open set. This is smallest equilibrium implementable. As a consequence, this outcome is going to be in the closure of the smallest equilibrium set. And I assert that this outcome maximizes the expected number of players that you can get to invest, conditional on being in the closure of the smallest equilibrium implementable set. Okay? It is a perfect coordination outcome. It has the feature that either everybody is investing or everybody is not investing. That's despite the fact that the game is asymmetric. Okay, so that's actually an important observation. If you care about all equilibria or the worst equilibria, you have to bring all the players together at the same time. Okay, now, why is this the best thing that you can do if you're trying to smallest equilibrium implement or fully implement? Okay, well, what I want to do at this point is just give you a hint of why it's the best thing that you can do. And I will give a generalization of this. I'll give the argument for a generalization of this a little bit later. Okay, so here's my hint. Suppose you look at this outcome, which I claim is the best that you can do. The best outcome in terms of getting players to invest if you need it to work in the smallest equilibrium. Well, suppose that the players receive a recommendation to invest. Okay, it will be a public recommendation to invest. They're both getting told to invest at the same time. We can ask the question, conditional on knowing that you've been told to invest, what's your expectation of the payoffs in the game? In other words, you assign 2/3 probability to the state being good, 1/3 probability to the state being bad. Let's take the average of these payoffs, 2/3 of this times 1/3 of that. What are you going to get? You're going to get this payoff matrix. What's the significance of this payoff matrix? Well, it's a complete information 2x2 game with multiple strict Nash equilibria. It has the feature that invest is just risk dominant. The definition of risk dominance, the Hassanian-Sultan game, one way of checking it is to say player 1 is prepared to invest when player 2 invests, as long as he thinks player 2 invests with probably at least 2/3. Player 2 is willing to invest if he thinks player 1 invests with probability at least 1/3. Because 2/3 plus 1/3 is less than or equal to 1, that makes this just risk dominant. And we know from the arguments of, well, generalizing the argument of Rubinstein and from the arguments of Carlson Van Dam for global games, there's something special about the risk dominant outcome. You can construct information structures that fully implement the risk dominant outcome. Okay, so that's my hint as to why this is the best fully implementable outcome. Okay, and the fully implementable outcome you can implement with global game. You know, in that case, you can implement with global games or an email game information structure. And when I prove the main result, we'll see a generalization of that logic to prove the main result. Okay, so let me take a few minutes to carefully describe sequential obedience, since this is the key condition in the paper, and then we can go straight to the main result. So I gave a verbal description of sequential obedience at the beginning of the talk. Let me try and give a more formal one. So intuitively, we care about who eventually plays one in the smallest Bayes-Nash equilibrium, but our definition of sequential obedience is going to be based on a hypothetical order in which players switch to choosing action one under an iterative procedure. Okay, so to define this, let capital gamma be the set of all finite sequences of distinct players of any length, including the empty set. Okay, so if the set of players are 1, 2, 3, this is the set of all sequences, sequences of length 0, sequences of length 1, sequences of length 2, and so on. Okay. An ordered outcome is a joint distribution over such sequences and the state of the world. For any such sequence, we can use this notation. A bar of gamma donates the action profile where player I plays action 1 if and only if he appears in the sequence gamma. Remember, you may or may not appear in a sequence gamma. Okay, so each ordered outcome is going to generate a regular outcome where you forget the order simply by merging together, just by forgetting the order, so just by merging together, by replacing the sequence with just the set of players who play one in that sequence. Okay, now let's write gamma I for the set of sequences in which player I appears, and write A minus I of gamma for the action profile of player I's opponents, where the other players play action 1 if and only if they appear before player I in the sequence gamma. Okay, so that's going to be the action profile that you sort of believe in when you get asked to choose. Okay, so here's finally is the definition of sequential obedience. We say that the ordered outcome is sequentially obedient if it has the feature that if you're player I and you're told to choose action 1, you ask yourself, given my beliefs over how other people are behaving in the state, do I want to choose action 1? And in order to decide that, you have to think through what could be the possible sequences in which people are being asked. Well, I'm asked, so I know that it's a sequence in which I get asked. But integrating over those sequences and the state, I will get a different payoff gain to choosing action 1, and I need the expected payoff gain to be positive, strictly positive, in fact. So sequential obedience requires strictly positive. Weak sequential obedience will be important too, where we replace strict with weak. Okay, so that's the definition of sequential obedience for an ordered outcome. We can also talk about an outcome being sequentially obedient if there exists an ordered outcome that induces that outcome. Okay, any questions about that definition? That's one definition that's kind of important. An important thing to remember is that there isn't a real sequence here. Don't get confused by thinking that there's a real sequence here. It's just the characterization. You'll see the role that the sequence plays in the proof in a second, but this is a story. This is an interpretation of the condition. All right. So if you remember the example that I had, invest with the best response for player 1 if he assigns probability 2/3 to player 2 having invested and probability 2/3 to the state being good. Okay, you can check that that's true. For player 2, that should say, oh, sorry. and not invest is the best response. This is wrong, sorry. This should say invest is the best response for player 2 if she assigns probability of third to player 1 having invested. Okay, so that means that we can construct an ordered outcome. This is the ordered outcome where either of the players, conditioning on them being included in the sequence, the only relevant sequences here are 2-1 or 1-2. Okay, so forget this possibility. Conditional on being in this box here, the question is, do you want to choose action 1? Well, if you're player 1 and you're advised to choose action 1, you think there's a probability when the state is good, conditional on the state being good. Well, actually, whether the state is good or bad, you always think there's a 2/3 chance that the ordering was this, and therefore player 1 has already switched to choosing action 1, which is exactly what we said you needed in order to make action 1 a best response for you. For player 2, it goes the other way around. He attaches probability only 1/3 to 1 having already chosen action 1. But this combination, this probability distribution over sequences, supports action 1 being a best response. So this ordered outcome establishes weak sequential obedience. This ordered outcome is weak sequential obedience. We could clearly perturb it a little bit to make the incentive constraint strict, and then we would have strict sequential obedience. Okay, just to give the connection between the example and sequential obedience. Okay, so here are the results. The main result of the paper, and the only result I'm going to have time to tell you about. If an outcome is smallest equilibrium implementable, then it satisfies consistency. It satisfies obedience, which is this condition that you needed just for partial implementation. Crucially, obedience requires that you have a best response to play 1 when you're recommended to play 1, and you have a best response to play 0 when you're recommended to play 0. But you also satisfy sequential obedience, which is this stronger form of sequential obedience required for when you play action 1. Okay, so those are necessary conditions. If we add in a weak additional condition, which is that the outcome that we're trying to induce assigns a probability, however small, to the dominant strategy state, then those necessary conditions are also sufficient. And as a corollary, if I can get an outcome to be implemented with a grain of dominance, since I can let this probability get smaller and smaller, the limit of those outcomes is going to be in the closure of the smallest equilibrium set. So actually, the closure of the smallest equilibrium set is going to be characterized completely by consistency, obedience, and weak sequential obedience. And I will use my last 15 minutes to prove this result. But any questions about it first? To sketch a proof, I should say. All right, let's start with necessity. So suppose it's the case that nu is smallest equilibrium implementable. There's an outcome such that there exists an information structure where the smallest equilibrium generates nu. How would I prove that? So by the way, consistency and obedience are immediate. So I'm just showing this as, from previous partial equilibrium results. So I'm trying to prove the harder thing, which is why is sequential obedience necessary. Okay, if nu is smallest equilibrium implementable, it must be the case that I can construct an information structure consistent, meaning it has the right probability distribution over the states, whose smallest equilibrium induces this outcome nu. Okay? There is such an information structure. Now we can ask the question, suppose we imagined players starting out all playing 0, and we imagined a iterative myopic best response dynamic process. So in particular, doesn't matter, these details don't matter, but suppose for concreteness, we took player 1, they're all playing 0, we take player 1 and we have player 1, for each signal, we'll have him switch from 0 to 1 if that is a strict best response given how everybody else is currently playing. Having done that for player 1, we then go to player 2 and say, given that player 1 has now switched and players afterwards haven't, you, for each signal, switch to player 1 if it is now a best response given what everybody is playing. And you go from 1 to I to player I, and then you do it again. You go round and round and round. Myopic best responses, myopic strict best responses. Okay? What's going to happen if you keep doing that? Well, that process will converge to the smallest equilibrium. Okay, this is a well-known property of supermodular games. Myopic best response dynamics from the lowest strategy profile will converge to the lowest equilibrium. And intuitive, I think. As long as it's not an equilibrium, somebody is going to switch upwards. And once it reaches the smallest equilibrium, nobody is going to switch upwards. Okay? So this says that we've just picked the smallest equilibrium implementable nu, any information structure that induces it, and we see that myopic best response dynamics will get us there. Okay, now by definition, okay, so here's a definition. For any signal or type of player I, if player I switches from action 0 to action 1 in the nth step of this myopic best response process, let's label that type n. Okay, so we label types by the round in which they switch from 0 to 1. Okay, if he never switches, we'll label that type infinity. Okay. Now, we're trying to establish sequential obedience, so we would like to construct an ordered outcome. Okay, a probability distribution over sequences and states. Well, here's what our ordered outcome is going to be. We're going to say that the probability of ordered outcome gamma and theta is simply the probability under the probability distribution of that information structure that the state is theta and that the profile of types are ordered according to gamma. What do I mean by ordered according to gamma? I mean that if you have a higher n, you appear later in the sequence. Okay? I'm going to claim that this satisfies sequential obedience. How would I do that? Well, first notice that because this myopic best response process converged to the smallest equilibrium, I know that this outcome, this ordered outcome, is going to induce the outcome that we started with. To show sequential obedience, note that for each type or signal of player I who switches, so who has a label less than infinity, it is obviously the case that it is a best response for him given his beliefs about the state and the types of others to switch given all the people who have, given that he thinks, given that he knows all the people who switched before him. A minus IT is defined to be the action profile of I's opponents in this myopic best response dynamics. Okay. So player I is expecting player J to choose action 1 if and only if the label of player J's type is below the label of player I's type. Okay. These equalities hold for each TI. Okay, but suppose we add up across all TI of player I. To put it another way, under the myopic best response dynamics, player I wants to switch whenever he's told to switch and he knows his type. But suppose he forgot what his type was and we simply asked him, I'm going to ask you to switch sometimes when I would have asked you to switch under the myopic best response dynamics, but I'm not going to tell you where we are in that process or what sequence got chosen. But because it was always the best response, whatever your type was and whatever the sequence was, it will continue to be a best response when we average across all those sequences. Okay, so it's kind of like a revelation principle argument, except on a slightly bigger space. That the only thing that we can add up what's happening across all type profiles with the same sequence, because it's only the sequence that really matters under the myopic best response dynamics. So that's it for necessity. Any questions? So now I want to show necessity. And I will describe it. And maybe the easiest way to describe it is to describe it as an analog of the email game, because a lot of people have seen the email game. So to establish sufficiency, I have to show how I'm going to use my properties of sequential obedience together with grain of dominance, consistency, and obedience to construct an information structure whose smallest equilibrium will induce the outcome that I'm trying to induce. Okay, so let's see how that works. So let's construct an information structure. I'll call it information structure 1 because I'm going to change it again in a little bit. But for our first information structure, let's construct an information structure. Let nu gamma be an ordered outcome that establishes sequential obedience, and we're going to use that in our design of the information structure. Let's draw a sequence gamma according to the ordered outcome. And let's draw an integer, a non-negative integer, with almost uniform probability. Okay, so we could have an exponential probability distribution with weight close to 1. So think of eta as very small here. Okay. Let the type of player I be given by m, that is the integer that just got drawn, plus the ranking of I in the sequence of gamma. Okay, he might be first, second, third, fourth, whatever. Just whatever that number is, it's m plus that number. And that's his signal or type. If he appears in this sequence. If he doesn't appear in this sequence, that's he's type infinity. Okay. Claim, suppose that we knew that the first K players were going to choose action 1 under this information structure, where K was bigger than the number of players. Okay? I'm going to claim an inductive step under that hypothesis. So if I knew that players earlier types choose action 1, I want to claim that types K plus 1 of all players must choose action 1. Why is that going to be true? Well, if you're type K plus 1 of player I, he knows that all players before him in the realized sequence gamma are playing 1 because they have types less than him. Remember how the types were drawn. We drew an integer m, and there's one m used for all players, and then their type is m plus their rank. So everybody has a higher rank than me is playing 1 by this inductive hypothesis. Okay? As eta goes to 0, his belief over what the true sequence is will be approximately the belief in the sequential obedience condition. That is to say, when eta is more than 0, you will be putting slightly higher weight on earlier states, and that will lead you to shift your probability distribution over sequences. But as it becomes uniform, your distribution over sequences will be exactly what it is under the ordered outcome that we started with. Okay, so that means that his action will approach his payoff to choosing action 1 in the ordered outcome that we started with, where by hypothesis, this is strictly more than 0. Sequential obedience requires that. Okay, so if we could only get action 1 to be played by the first I types in this information structure, we would be able to get action 1 to be played by all types, and that would then be the smallest equilibrium. Okay. Sorry, not by all types, by all types other than type infinity. But that's what we need to do to implement the outcome. We need to get it played by all types other than types infinity. Okay. Now we can construct an information structure 2, and I'm not going to give the details of this, but basically we can rearrange the payoffs in information structure 1 so that these early types have a dominant strategy to play action 1. Why do I know that I can do that? Okay, so I need to keep those incentives strict for all the types other than the first K types in order to let the sequential obedience conditions lead to the infection argument. But I perturb the payoffs of these first K types. Why is it possible? Well, first of all, we assume grain of dominance. So there is some positive probability on a state where it's a dominant strategy to choose action 1. And if we choose eta sufficiently small, it means that the ex-ante probability of those first I types is becoming arbitrarily small. Okay, so this probability, however small it is, will be large relative to the probability of those first few types as we take eta closer to 0. Okay, so basically that's why we can do it, and that's the proof. And I think I will just stop. Oh, let me give this slide. So the sequential obedience characterization is kind of cute, I would claim. Let me finish with this slide. It gives rise to a finite linear program, and it sort of sounds like the obedience condition. But what is it good for? It's pretty abstract. It doesn't immediately tell you things. There is a fair amount of extra work to deliver concrete characterizations in particular games, but you can actually get a lot of results. So in the paper, we derive progressively simpler characterizations of sequential obedience, which we call coalitional obedience and grand coalitional obedience, that hold under additional assumptions, and then you can prove more concrete characterizations in particular settings. and I will stop that. Any questions?
So many thanks for Stephen. Any questions about the talk?
Good. Perhaps I have one, sorry. So Stephen, so in your sufficient direction, so sufficiency part of the proof, so do you have a counterexample that this grain of dominance is needed
Yes.
for your result?
Well, exactly what we need is not, so it might be a tiny bit stronger than what we need, but an easy example of why you need something is consider a game in which at every state of the world, if it was common knowledge, all play 1 and all play 0 would be Nash equilibria of the complete information game. Then there will be an equilibrium where all play 0 and an equilibrium where all play 1. Definitely. And that's independent of sequential obedience or obedience or anything else. So there has to be something that gives power to these things. Now, our grain of dominance said that every player had a dominant strategy there. That's clearly a little bit too strong. We do need at least one player to have a dominant strategy at some state. And then we would probably need a second player to have a best response to choose 1 if he's sure, if he thinks we're at the state where player 1 has a dominant strategy and he's sure that player 1 is choosing action 1. So grain of dominance could be weakened a little bit, but something of that flavor is definitely required.
Okay. Thank you.
More questions?
There is a question in the chat. What happens if there are more than 2 actions, or when is 2 actions used in the proof?
Excellent. So if the game is supermodular, so if the game is not supermodular, clearly it was heavily using supermodularity all over the place. But if the game is supermodular and there are many actions, then there are clearly some things that we can do. What we would be able to do is come up with a definition of sequential obedience, which would sound a little uglier with many actions, but would be essentially the same idea. So instead of having players, having a sequence and when do players switch from action 0 to 1, you would look at any path by which the profile of actions moved up, and you would be moving up 1 action at a time or more than 1 action at a time. You would basically look at paths by which players switched up to the first equilibrium, and you could define a sequential obedience condition. So necessity of some more complicated to state sequential obedience condition you could get. For the sufficiency argument, our construction uses, so we don't know how to do that with many actions if it's supermodular. I mean, what you would need for the general sequential obedience condition, what you would need would be to saying, holding down when does a player switch 1 action at a time and when does he switch 2 actions at a time, and how to construct an information structure that's going to reflect that. We don't know how to do. So, but that, I mean, it's perfectly conceivable that you could do that, but it is going to be a little bit more complicated at least.
Okay, thank you very much. If there are no additional questions, then I will thank again Stephen for this very interesting talk. And we'll meet again in 2 weeks. So thank you very much, everyone.
Thank you.
Actually, we meet next week.
Next week there is the workshop, right?
Yes, and it ends with a special talk of the One Word seminar.
Yeah, and the workshop is between when and when, Galit?
Oh, yeah. Good question. Wait. Unprepared for the question.
12, but I'm not sure.
Marco, what did you say?
I think it starts at 12 European time, Central European time, but I'm not totally sure.
Yes, I will check. I will check in a minute. It appears on our website. Wait. I will send also an email with the abstracts and all, because I have most of them now, with the schedule and the abstracts.
Starts at 12:20.
12:20, yes, exactly.
12:20, and this extra talk by Kostis Daskalakis starts at the usual time at 15. So 3 o'clock, the Central European time.
Okay, so see you all again next week.
Yeah.
And have fun and stay safe.
Thank you.
Bye.
Thank you. Bye-bye.
Thank you.